Hi, my name is Amanda Price, and I want to thank Dr. Zolkowski for giving me the opportunity today to speak to you about some of the research that I've conducted in the past as a way to hopefully demonstrate how some of the concepts you're learning in this course are actually carried out when folks are conducting research. The work that I'm going to be talking about today is work that I did with elderly people, men and women, who had Parkinson's disease, and I was comparing that group to a control group of roughly age and gender matched folks who did not have any kind of neurological or psychological issue. I believe right now you all are generating ideas, or maybe you've gotten past that stage and you've started really thinking about a particular research idea. Now, the way that my process had worked is that over the course of a number of years, certainly not just a couple of weeks like you guys have, I was able to basically read virtually everything that was out there on my particular topic, which, as you can see, was this issue of how people who have Parkinson's disease or damage to the frontal lobes more generally perform on problem-solving tasks. And the reason why I combine these two things, frontal lobe and Parkinson's, is because Parkinson's disease typically results in some frontal lobe dysfunction. All right, so I read everything, virtually everything on the topic, and in doing so, as is often the case, I found some conflicting evidence. Some people said that problem solving was normal, others said that it was impaired. And this is always good. When you see some kind of conflict, one of the things that lets you know is, all right, this is a research area that's ripe for more research, for more study, to better understand why is this conflict emerging. So what I did was looking through those articles, reading what the researchers had to say, and then doing some of my own creative thinking, came up with possible explanations for why that conflicting evidence existed. One of the possibilities is there might have been some group differences. Maybe some studies had more patients with greater severity in their disease, and maybe they were the ones that had impairment. Other studies that had less impaired Parkinson's patients, maybe they did just fine. So that's a possibility. Another possibility is that not everybody is using the same task, and so maybe there's something in particular about the type of task. Maybe Parkinson's disrupts certain types of problem solving, but not all types. And so those are my two big ideas. There were other possible ideas out there, but those are the two that I really wanted to tackle in this study that I'm talking about. And then what I wanted to do is I located additional research that supported my potential explanations, because that's what I was going to use in my introduction section as well as in my conclusion section, because of course science needs to build on itself. So we don't come up with ideas out of the clear blue. Our ideas are supported by previous research. All right, so here's the phase that probably many of you are in with the project that you're proposing for the course. Once I had my ideas and I had some theoretical foundations for those ideas based upon my previous research, it then became necessary, of course, to create a methodology. Now, one of the things that I have tried to encourage students in the past when I taught various methods courses is that there's no reason for you to reinvent the wheel. If other people have used a method, it's been approved, it's standardized, there's no reason why you should have to come up with an entirely new methodology. So for example, there might be surveys that are out there, tasks that are out there that are used across many, many studies. Basically, other researchers have given that method their stamp of approval. And so that's why I have on here, if somebody else did the technique, then borrow it. And in fact, I've had students who have contacted researchers at Dartmouth or UCLA or Washington University and said, hey, I'm really interested in using this computer task that you created. Would you be willing to share that with me? Or I'm really interested in this survey. Can you share that? And typically, unless the researchers are selling it elsewhere, they are happy to share with students. Now, I want to be clear, I'm not saying that you can just read an article, go, oh, wow, that's really interesting. I'm going to do exactly what they did. Excuse me. But quite often in science, we will take a method, tweak it a little bit, or maybe combine a couple different methods, or maybe do a task on a new population. And so in that way, we are doing that gradual building process that's so fundamental in science. So I took a pre-existing task that I think some guys out of Dartmouth had been using modified it a little bit, and I'll talk about the task in a few minutes. And then I added a couple other pretty standardized tasks to this one. So what I needed to do in order to really get a good handle on my method and a good handle on how I was going to collect and analyze my data is that I had to operationally define my variables. I'm assuming this is a concept you've already gone over. An operational definition gives you a way to actually quantify, to actually measure some maybe abstract concept. So here are all the various concepts that I was interested in looking at. And all of these, and I'll talk about them in a little bit more detail here momentarily, all of these things that I have listed here are components that I and other researchers were confident might be part of the problem-solving process. So I had to come up with a task that would allow me to measure how good is this particular participant with his working memory, or how good is his ability to inhibit concepts and ideas. And I'll talk more about how that was operationally defined. I also needed to have some way to quantify or define Parkinson's disease. Now, the nice thing is there are a number of standard measures that are out there to measure Parkinson's disease, and so I used two of those as patients came in to measure their motor and cognitive difficulties. I want to speak a little bit about the primary task that I used, and this is the way that I was quantifying self-directed cognitive flexibility. You can see, hopefully you can see I'm using an anagram task where people were given a set of either 5 to 6 letters, and they had to unscramble them to create a word. And what I was trying to do was create 3 different versions that would vary in terms of how much self-direction a person needed in order to complete the task. So in the baseline version right here, there are no clues provided at all. And so this relies very heavily on the person's own internal self-direction to generate a solution. Now, these other 2 versions right here provide people with either a conceptual or category cue or some kind of physical cue right in front of them that would help to push them towards a particular solution. And so in that way, these 2 right here don't require as much self-directed cognitive flexibility. So what I would expect is if you have a particular problem with doing that self-direction, you will suffer, you'll be slower at resolving these tasks than you would at resolving these tasks right here. For those of you who are trying to figure it out, if you haven't already, the word right here is apple. Word over here, number 1 thing that tends to pop into people's minds is hammer. And this one right here, which is the number 1 thing that tends to pop into people's minds if I say name a thing that's green, is grass. And I know that it's the number 1 thing because there's actually research out there that I relied on that studied hundreds of people and said, all right, tell me the first 10 things that come to mind when I tell you to list tools. Tell me the first 10 things that come to mind when I tell you to list fruits or things that are green. And so these words that I used were not just accidental. I chose these words very specifically based upon word norms. All right, so just a little bit of, I guess, nerdy information there for you. Now I'll go back to this list. The next thing that I needed to operationally define is working memory. So this is kind of like short-term memory. It's your ability to hold information in mind and manipulate it a little bit. This is another place where we see Parkinson's patients experiencing problems. Looks like that link did not work. And my measure of working memory is that I would have people do something known as the computation span task. Again, this is a standardized task that has been shown to be a very good measure in older folks, a good measure of their working memory. The way that it works is you have a whole series of math problems that are done, and what the person has to do is they see this problem here, and they say, okay, 4 plus 2 equals, and they're going to choose 6. All right, so that's the first step. The next thing that they have to do is they need to hold this second number in mind, 2, because later on I'm going to test them, and I'm going to say, all right, tell me all of those second numbers. And so what they're having to do is hold information in mind, but also do some mental arithmetic. And so it can be a demanding task, especially for older adults. Right, so they see this problem, and then they see this problem, 5 minus 3 equals 2. So now you have to hold in mind 2 from up here, 3 from down here, and then I tell them to recall, and so they would be asked to write 2 and 3, ideally in that order. Some of my older folks could only do as well as just holding these 2 numbers in mind. The test actually goes all the way up to having 7 math problems, and so then you have to recall 7 numbers. Very few people can get up to that point. That requires quite a bit of working memory to do. So most of my folks with Parkinson's were recalling maybe 2 or 3 numbers, which indicates they had lower working memory than other people, my healthy folks. Okay, semantic fluency is a third thing, and again, there is a standardized test to measure this. What it refers to is how quickly you can come up with words, basically. So semantic is essentially the word for word or meaning, fluency meaning how quickly you can do something, and I would give my people a letter of the alphabet. In particular, I would say F, and they would have to list all of the words they could think of that started with the letter F, and they had 60 seconds to do that. The idea is that if you have a good degree of cognitive flexibility, you're pretty good with that self-direction of generating things on your own, you're going to be able to come up with quite a few words. The difference classically is that my healthy older adults might be able to come up with an average of 15 words in a minute. My Parkinson's patients are maybe coming up with 10 to 12 words in a minute, and that is a reliable difference. Next thing I wanted to measure was inhibition. My links are just all wrong. Okay. Again, I'm using a very standard task. This is a fun one. So a very standard task of inhibition, and inhibition refers to the ability to control or inhibit one action so that you can do something else that's maybe a higher priority. So in this thing, it's called the Stroop task. There's 2 different conditions. In both conditions, what you have to do is name the ink color as quickly as you can. So red, blue, green, yellow, yellow, green, blue, red, yellow, blue. Easy, easy, easy. All right, now the big test, though, comes with this next phase. Now you still have to name the ink color, but I guarantee you would be much slower. So this one would go green, yellow, red, blue, green, blue, red, yellow, yellow, blue, red, green. It was pretty clear, I think, just in the rate with which I was reading that you could tell that I was slower the second time around, and everybody is slower. And the reason why we're slower is because in order to do this second version, we have to inhibit the natural desire to just read the word. We're very automatic at reading. We inhibit that in order to actually do what the task demands of us, which is name the ink color. Now, everybody's slower, but as we get older and older and older, this task becomes increasingly difficult because our ability to inhibit that tendency to read, that inhibition fades. So sometimes what I would hear in some of my older folks, or particularly with people with Parkinson's disease, is, well, either I would see their mouths moving as they were reading, or I could almost hear them say, red. And they would have to try to inhibit that desire in order to say green, in order to say the ink color. And so typically as inhibition declines, we see a much bigger jump in time that it takes to do the second versus the first version. And also people make more mistakes on this second version. So I've come back to this main menu. Inhibition, as I've defined it, is with that Stroop task, looking at the difference in times between the first and the second version, and also the number of mistakes, the difference between the first and the second version. So that gives me a really nice way to quantify inhibition. The final thing that I think was a component in problem solving is mental set shifting. So what set shifting involves is a lot of times as we do a problem, we get kind of stuck in a rut, stuck in a routine, and that's our mental set. And what we need to do sometimes is put a hold on that mental set and go ahead and do something different. One of the classic ways of measuring set shifting, mental set shifting ability, is this card game known as the Wisconsin Card Sort Task, WCST. And it's an interesting little game. What happens is people have these 4 key cards, and they need to decide where to put a card in a new deck. Now, I don't tell people any of the rules. So if you notice, you could put this card right here. If you wanted to match it according to red, you'd put it over here. If you were matching according to number of symbols, you'd put it over here. If you wanted to match based upon the type of object, you'd put it over here. Now, I don't tell the participant what kind of category I have in my head. I would typically start with color, but they didn't know that. So they would make matches, and if they put, my cursor, if they put this over here and matched by object type, I would tell them they were wrong. All right, well, a healthy person is going to say, all right, object type wasn't the right mental set. Let me go ahead and shift to something new. And so maybe they would choose color and put it over here, and then I tell them right. All right, so then the next card comes up, and they should still be matching by color. Color, 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 and then all of a sudden, bam, the rules change. So they're matching by color, and I end up telling them wrong. Okay, in healthy people, even though they had built up this nice routine, this nice mental set of matching to color, if you get told you're wrong once or twice, you start thinking, maybe I need to try something new. And so then you might try matching according to number or object type. But what I would see in some of my older folks, and especially among the people with Parkinson's, is that they would continue to match with color, and they would continue to get told, sometimes over the course of 50 different cards, wrong, 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 wrong. And it was either that they were just stuck and they were sorting by color, or they just really seemed to have a hard time arriving at a new mental set. So this gave me a good way to measure how flexible a person is. Are they able to change their mental set? And that was a key component in what I think is affecting problem-solving ability. And then I already mentioned that I had a couple Parkinson's disease measures as well that I'm not going to get into here. Okay, so I moved on, and I wanted to talk a little bit about determining how reliable and valid your tasks are. And one of the really wonderful things about using standardized tasks that have been used by other folks is that often there are data on how valid and reliable that test is. So those standard tests that I was using, I already felt really comfortable that they were valid and reliable because other people have done the research to show me that it is. Now the anagram task that I was using was developed by another group, and I tweaked it a little bit. So I needed to take some additional measures to make sure that this is really measuring what I wanted it to measure. A couple things that you can do is some background measures to just make sure that this is the best possible task you can get. I already told you a little bit about using those word norms. I wanted to do that to just make sure that all of my different anagrams were equally challenging, that all of the words I was using were equally likely to come to mind for a person. So I wanted to make sure that my various anagrams were really comparable to one another. Another thing that I did to make sure that all of the anagrams were easily solvable was to pilot test it on college students. So you can see one guy here who's working on the anagram task. And so if I had a couple trials where people just were really stuck and they just could not solve the word, then I threw it out. Because certainly if my college students couldn't do it, I expected that my Parkinson's patients would certainly have a problem. Another really important way to help validate a task is to repeat it several times. So each of those phases, the baseline anagram, the letter Q, category Q, I had multiple test trials. And so that was really nice because, again, if a person got stuck on one word, that wasn't their only way to demonstrate their problem-solving ability. Certainly you wouldn't want the only way you are assessed in this class to be a single exam. That's probably not going to be a very fair measure of your ability. So just like you have multiple assessments in a course, my participants had multiple assessments, multiple test trials. Another issue with internal validity is that if my test reveals that there is indeed a different level of performance in my Parkinson's group, which I'm calling PD, and my healthy control group, which I basically abbreviate with NC, normal control, if I see a difference between those groups, Does it actually reflect problem-solving ability? Or might it reflect something else? Some other difference between my two groups that has nothing to do with problem solving. So I want you to pause the video now and give some thought to these two questions. First of all, can you think about any additional measures that one could take to ensure that the groups are as similar as possible, to make sure that we can try to eliminate all of those confounding variables, variables that could lead to a group difference that have nothing to do with problem solving. So how might we try to eliminate or minimize group differences? And I also want you to think about, perhaps it would be better to answer this question first, what differences might exist between the PD, Parkinson's, and normal control participants. So what differences, what confounding variables might exist that could trigger a group difference? So give some thought to that, come up with some ideas, and then go ahead and resume the video. Okay, well, I've never opened up a question for group discussion and not been there to facilitate the discussion. So, of course, I have no idea what ideas you came up with. But to answer the first question of how might we go about ensuring that the two groups are as similar as possible? Well, ideally, we would do random assignment. That we can't do that here. But that is the best way to ensure that your two groups are as similar to one another as possible. And of course, the way you would do that is with each participant that comes into your lab or into the study, you basically flip a coin. Heads goes to group A, tails, you're going to go to group B. But of course, I can't flip a coin and arbitrarily decide if George Jones has Parkinson's disease or not. So technically, the thing that I'm describing to you is not a true experiment, but a quasi-experiment, because we can't do random assignment. So since we don't have that, the next best thing, and the thing that's commonly done, is to try to recruit similar types of people. The easiest way for me to do this, and often the way it's done in other studies as well, is we recruit people with Parkinson's and their spouses, or people with Parkinson's and maybe a sibling. So in the study, people tended to come in as duos, and we would test the two of them at the same time in separate rooms. Now, ideally, by doing this, especially if you have spouses, the idea is that they're going to be similar on a number of variables. And so that was the second question that I had posed to you, is what sorts of things would you be worried about that might trigger a group difference? So I tried to make sure that my groups were as similar as possible on a couple variables, because I was trying to minimize the effect of these confounding variables. So I wanted to make sure that my two groups had equal numbers of men and women. A big reason why I did this is that we know that women do better on the semantic fluency task, the one where you list words that you can think of that start with a certain letter. And just generally, it's useful to try and make sure that you have a similar ratio of males to females in each group. Parkinson's disproportionately affects men, so I had a higher number of men in each group. I also wanted to make sure that they were similar on age. This is why getting spouses can be so helpful, because certainly as we get older, our cognitive function declines. That is a general truism, and so I wanted to make sure that I had a similar age range. I think the average age in each group was probably about 68 or something like that. Then I wanted to make sure that they were really comparable on premorbid IQ, meaning I had to get some kind of estimate of their IQ prior to getting Parkinson's disease. And there's actually a really simple test. It's a little reading test where people actually just read unusual or rare words. And the idea is that smarter, more intelligent people will be more well-read, will have a better vocabulary, and will be familiar with more words than people of a lower IQ. And this is a case of validity where this reading test is actually highly correlated with much larger standard tests of intelligence. So I measured that, made sure my two groups were similar in terms of general IQ. And a final variable that I was interested in was level of depression. And there is a standard geriatric depression scale that I used. And so this way I wanted to make sure that if somebody was doing poorly on problem solving, it wasn't simply because they were depressed. And that's a very real thing that can happen. I will tell you that although I would have liked both of my groups to be comparable in terms of their mood or their level of depression, the reality is my Parkinson's group did have a significantly higher score on the depression scale. However, depression was not correlated with their problem-solving ability. But that was a potentially confounding variable. All right, when we're talking about internal validity, what we're referring to is, does your test measure what you think it measures? And in the previous slide, I talked a little bit about group differences and issues that can come up with confounding variables in terms of the differences in groups. In this slide, I want to look at the task itself. And there is the possibility that, let's say I see a difference in performance on one of my anagram task versions relative to the other ones. Okay, how do I know that that task difference reflects something meaningful about my participants' actual ability? And how do I differentiate that from some kind of task difference coming up that's really just a fluke? Okay, so let me go ahead and take a look at the task itself now. All right, so this is what I talked to you about before. We have 3 different versions, and let's say I tested everybody. Everybody does this no cue baseline task first, then they do the category cue task second, and then they do the letter cue task third. Can you think of any reasons why people might always do well on one particular task that has nothing to do with actual problem-solving ability? But maybe they perform better on the first task, or maybe they perform better on the second or the third. It has nothing to do with problem-solving ability. Can you think about any other reasons for a difference in performance on these 3 tasks? And then as a second question, is there anything that an experimenter can do to try to ensure that each of those 3 time points or each of those 3 tasks is basically on equal footing, so that if we do see a difference, we can feel pretty confident that it has to do with problem-solving ability? So I'll open it up for group discussion now. All right, you probably came up with a couple different ideas. My guess is you maybe came up with something along the lines of these 2 things right here, practice effects or fatigue effects. So if we have 3 slightly different versions of the task, it's entirely possible that folks are going to get better and better and better just because they've had practice solving the anagrams. And so if we just see that people are improving over the course of time, we need to be mindful that this could just reflect practice. On the flip side, it might be possible that we see folks getting worse and worse and worse, and that could reflect what's known as a fatigue effect, where as the task goes on, this lasts about 30 minutes, people just get tired and they lose the ability to focus very well, and so they're going to do progressively more poorly. In any event, these are all collectively known as order effects. And so it is a very bad idea to have 3 different versions of the task and have people do those versions in the same order. The thing that we can do is a phenomenon known as counterbalancing, where basically each person gets a new order of the tasks. So for example, George would first do the category cue task, and then he'd do the baseline no cue task, and then the letter cue. And then I would mix up that order for his wife, Mimi. And then Fred would come in and he would do yet another order. And I made sure that basically all of my Parkinson's patients had different orders. All of my control patients did the tasks in different orders, so that you can see in this place the first task, sometimes it's the concept, sometimes it's no cue, sometimes it's letter cue. So if folks are consistently doing best on the letter cue, I know it's not just because it happened to be first, because you can see the letter cue task is occurring in different places. And that's a phenomenon known as counterbalancing, a really nice way to get rid of these little order effects right here. Another thing that we need to do to make sure that our study is actually testing what we think it's testing is we need to eliminate, or at least minimize, experimenter bias. And I guess the deep dark secret of science is that we like to claim that it's not biased, that scientists are fair and impartial, and that's simply not true. For example, If I truly believe that my Parkinson's patients are going to have a problem, I might treat them differently. I might give them some extra help. I might give them extra instructions. I might give them extra time. Or I might assess their performance slightly differently than I do my control patients. And I may not even realize that I'm doing it. So ideally, what we would have would be a double-blind study. You've probably come across this before, but ideally with a double-blind, and I thought this was a cute little graphic, with a double-blind study, the participant doesn't know which group he's been placed in, and the experimenter also doesn't know which group that participant has been placed in. Now, that's the ideal thing, but quite frankly, no person is unaware of the fact that they have Parkinson's disease. So it makes it impossible for the person to not know which group they're in. And also, for me or even my research assistants, we always knew who was coming in and who among them belonged in the Parkinson's group. They shuffled. They walked really slowly. Their handwriting was really slow. Their faces didn't really move that much. You know when you're looking at somebody who has Parkinson's disease. So I couldn't make the experimenters blind to group assignment either. So double blind, just even a single blind, wasn't possible here. All right, so what steps can we take to try to reduce experimenter bias? One of the things, as I mentioned, that I had students collecting the data for me. And although they did know who had Parkinson's and who didn't, they didn't know my hypothesis. They didn't know what I was shooting for. And I've also found that research assistants, their main goal is to try to do a good job to please their professor. They don't really feel a need to cook the books, if you will. They just want to do the best job possible. And so that's a really nice way. By not telling them what my hypothesis was or what I was hoping to find, they were less likely to be biased. Another thing that I did is I had a standard protocol. There was a handbook of instructions that these students basically read from. Didn't matter which type of person they were talking to, they followed that same protocol. And then finally, wherever possible, I had the computer collect and analyze data. So a lot of my experiments, Wisconsin card sort, Stroop task, that anagram task, all of that was done by computer, and you would not expect any experimenter bias going on in a computer. So these were the steps that I tried to take. Are they ideal? No, but they were kind of the closest I could get to eliminating experimenter bias. All right, now I want to switch gears away from internal validity and that issue of, is my experiment measuring what I think it is, and move towards external validity. External validity refers to generalizability. So essentially what that means is, with the results that I found with the 15 people that I recruited who had Parkinson's disease and the 15 people that I recruited who were healthy older adults without Parkinson's. I recruited them in 2007, Central Pennsylvania, from 3 different support groups in the area. And they came in, did my study for, I think I paid them $20 or $30 for their 3 hours of time. That little group of 28 people, with the results that I got from them, can they be generalized to the entire population of people who have Parkinson's disease and people who don't? All right, that's the key question of external validity. And so if you look at this graphic right here, ideally what we want to believe is that we take this tiny little sample and the results that we get from them can be generalized back and tell us something about the population in general. And so for this next discussion question, I want you guys to spend a few minutes and think about what might be some problems. What critiques would you make that would lead you to say, I'm not so sure that that sample is fully representative of the entire population of folks over 60 who have Parkinson's and folks over 60 who don't. All right, so spend a few minutes and think about that question. Pause now, and we'll come back and I'll talk about it. I imagine you all came up with a whole host of ideas on why that particular sample would not be easily generalized to the entire population. There's a couple things I just wanted to hit upon. One of the things is, ideally, when we do a study, we would love to be able to get a random sample, just willy-nilly picking names out of a hat, out of a phone directory or something like that, and getting a truly random sample of people from the population. Almost no study does that. There are some really nicely designed epidemiological studies that accomplish this, but most research just can't. So if you think about it, I was recruiting from a very focused area. I was recruiting from support groups. And so what kinds of people might be volunteering for my study? Well, it's people who are really curious about their disease. They're going to support groups. They're trying to be educated. They're being really proactive. And they're volunteering for research. So that tells me that these people are a little bit different. They're more intelligent. They're more proactive. They're more curious than maybe the general population of people with Parkinson's disease. It's also important to keep in mind possibly the effects of time and location. So this study was done in central Pennsylvania. It was done in 2007. And there might be something unique about the type of people who have Parkinson's disease in central PA at 2007. And that might be different than the people who are living perhaps in Silicon Valley, or the people who are living in Idaho at different points in history. And these aren't necessarily things that I would bring up in the conclusion section of my study, but as an educated reader, it is important to just be mindful that the external validity of this study and a lot of other studies that don't have a random sample from the entire population have some limitations on their generalizability. All right, so I talked a lot about methodology because that was really what Dr. Zolkowski wanted me to hammer home, but we're nearing the home stretch, and so I'm going to talk to you a little bit about the conceptual issues, developing my hypotheses. And in this study, I had a couple different things that I was interested in. One very basic hypothesis is I wanted to know if the previously noted impairment to problem solving would generalize to these new arrangement or anagram problems that I had come up with. If that's the case, my hypothesis is that if that's the case, Parkinson's patients would not do as well as normal controls overall. Regardless of which task type we're talking about, they're going to struggle on the anagrams. All right, but quite frankly, I was predicting that they wouldn't struggle overall with the anagrams. And so I was predicting that there was something a little bit more specific or more nuanced. If the Parkinson's impairment reflects a problem with generating solutions on their own, going back to that self-directed cognitive flexibility, doing something on your own. If that's the case, I expected that when I gave Parkinson's patients cues, the letter Q, the category Q, they would do better than they did on the baseline. So basically, if they have a problem generating solutions on their own, I give them clues, they do better. And I had also made the prediction that anagram performance would correlate with tests of semantic fluency. That was the one where you had to generate the words. That's something that really demands a lot of self-direction. So if self-direction is really the key problem, we should see this correlation right here. And then as my third hypothesis, I expected that if the Parkinson's problem-solving impairment reflected other aspects of cognition, set shifting, inhibition, working memory, then anagram performance would correlate with those measures that I talked about at the beginning of today. And before you can really analyze the data, you need to do what I actually consider to be the fun part, the statistics. And I imagine you all may not share my love of statistics, but I always kind of find it to be a bit of a treasure hunt, and that's why I have this little guy here with the magnifying glass. The first thing that a person has to do is clean the data. Because I collected a tremendous amount of data. I said before that I had many trials of the baseline task, many trials of the cued task. And so I had to combine them together because I wanted an overall mean. I wanted to know, how did George do overall on the cued task? Give me a number. How did George do overall on all of the trials of the no cue task? One number there. And I was looking at reaction time and accuracy. All right, once I combined my trials, I then looked to see, were any of my people outliers? So outliers is classically defined as being 2 standard deviations away from the mean. So if the mean level of performance is that it took people on average 8 seconds to resolve an anagram, and George was taking 16 seconds, that would be much more than 2 standard deviations, and I would have actually removed George from the study because of his outlying performance. I don't want him to mess up my means. That, you know, he might have been distracted, he might have been really tired, there might have been something going on with his meds, I don't know. But I don't really want to let outliers disrupt the performance. And this is a very typical way to clean the data. And all of that data was entered into a statistical software package, similar to the type of software that you're using to analyze your data when you do statistics class. So SPSS is what I was using. Nice thing about SPSS is you don't have to do any hand calculations. It gives you your means, your standard deviations, your t-test values, your p-values, your correlations, all that fun lingo you're learning about in statistics. SPSS goes ahead and spits out your means, your graphs, and you can go ahead and run the statistics that you plan. So my planned statistics were determined by the hypotheses that I showed on the previous slide. And then, here's another little dirty secret about science. You don't just stop there. Instead, after you invest hundreds of dollars, many hours, you've taken these people's time and energy, you want to get as much out of this study as possible. And so the reality is, after you run the planned statistics, you then run every other test that you can possibly think of that might be remotely interesting. And so you might call this data mining. Other folks just call it a realistic, good way to use your resources. There are some statistical corrections to kind of separate the difference between planned statistics and those ad hoc statistics, after the fact statistics. I won't get into that. The final thing I will show you is the actual data. If you recall from the hypotheses that I had mentioned, one of my major predictions is that people with Parkinson's would have really major problems when they had to solve the problem entirely on their own, when it required a lot of self-direction. And what we see is on that baseline task where they didn't have any cues, the Parkinson's patients were definitely performing more poorly than the controls, and that was supported by the t-test, and you can see the p-value is really quite low, telling us that this is a reliable result, that Parkinson's patients were indeed slower than controls. And we can compare that to the task where there was a letter cue, and in this case, when there was enough support so that the Parkinson's patients didn't, or that all the participants didn't have to rely on self-direction, well, it helped the controls a little bit, but it had a huge benefit for the Parkinson's patients. And there really was no group difference at all, and that's supported by our statistic down here. A high p-value means there's really no reliable difference. So that tells me that the hypothesis about self-direction and its role in problem solving for Parkinson's patients was true. And then we can also look at some of these scatter plots with correlations. What we're looking at here is the FAS test. So that was where I said I give you a letter F and you have to name as many words as you can think of. What we see is a negative 0.64. So 0.64 is pretty high for a correlation in psychology. The negative simply means that as one variable goes up, the other variable goes down. In this case, we see that people who did really well at generating words were also the ones who happened to be really quick at resolving the anagram. So that tells me that this test of self-directed cognitive flexibility was very much correlated with my problem-solving task, which I thought really depended upon cognitive flexibility. We also see a correlation between inhibition and anagram performance. So the people who had the strongest amount of inhibition and therefore didn't do very much worse on that second Stroop task tended to resolve the anagrams pretty quickly. Those who had low inhibition tended to resolve it rather slowly. These tasks of set shifting and computation span, which was the working memory, these measures of 0.2 really aren't very strong at all. So that tells me that set shifting and working memory aren't involved in the the anagram task. That concludes the presentation at this point. I would love to take questions from you all, but of course I am unable to be there today. If you do certainly have questions that you're curious about, please do pass them on to Dr. Zolkowski, and she can email them to me. You're welcome to email me. My email is ap027, and I'm certainly happy to get back to you. I appreciate your attention and wish you a good evening.